Hello everyone! In this video we will continue examining topic 7.1 discrete energy and radioactivity, and in particular we will focus in on nuclear physics. So, nuclear physics is a phrase or a subject that many people have heard of, particularly in the context of nuclear bombs, either in the discussion of nuclear bombs in history or perhaps nuclear power. In thinking about energy and power generation. But it's important to recognize that the nuclear part of nuclear physics actually has a direct meaning. Nuclear physics is the physics of the nucleus of an atom. And the physics of the nucleus of an atom is sufficiently different from the rest of physics that in truth it will occupy us for a lot of the next topic. Simply put, what goes on inside the nucleus is of a different sort and requires different physics to describe it. So we're going to narrow in on this structure of the atom. Up to this point, we've discussed atomic physics in the context of energy levels, as revealed through emission and absorption spectra. We know that the electrons exist in discrete energy levels outside that central nucleus. But we're going to begin with sort of the process of unpacking that structure of the atom and a reminder of a whole bunch of terminology that is probably familiar to you from chemistry. Of this terminology, much of it we will continue to use. There will be a little bit more that is new. And then there will be some terms that we can use either the chemistry term for or the physics term, and I'll go through those as we get to them. So in the basic structure of the atom, we have the negatively charged electrons, the outside, and then those much larger, at least mass-wise, protons and neutrons located in the central nucleus of the atom. And those protons and neutrons are very, very tightly bound and very close together. And that already suggests to us that we will need new physics to describe what's going on. Why? Because those protons should be repelling each other. And in fact, they do repel each other. It's just that there are other forces and interactions at work at nuclear scales that are keeping those protons and neutrons bound. And so in this subunit, we will begin to discuss why that is and how that works. First, a quick reminder. The nucleus of the atom at roughly 10 to the negative 15 to 10 to the negative 14 meters is very, 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 very small compared to the overall size of the atom. The overall size of the atom, as measured sort of by a rough radius of where the outermost electrons are, varies from roughly 10 to the negative 10 meters at its smallest to as large as 10 to the negative 12 meters for larger and larger atoms. This difference right here, the difference between the size of the atom and the size of the nucleus, seems to us from our lofty macroscopic height as being, well, they're both very, very small, but it is important to recognize that that is a factor of 10,000 to 100,000 times smaller. The nucleus, with all of that mass and the two protons, in this case, for this particular atom, notice this is a helium atom, is not just a little bit smaller, it's so much smaller than the general size of the atom as to sort of render the idea that atoms take up space almost comically odd. Okay? Because while atoms push against each other, the particles that compose the atoms are much smaller than we consider the size of the atom itself. At 10 to the minus 10 meters, the actual sort of meat, so to speak, of the atom is located in that central nucleus at 10 to the negative 14 meters wide. This is incredibly small. But the neutrons and protons are located in that nucleus, and in fact, there's a term that physicists use when referring to neutrons and protons known as nucleons. And nucleon is simply a term that means sort of a particle that could be in the nucleus. Neutrons and protons are both nucleons, whereas electrons are not, because they are not located in the nucleus. So, given this general structure for an atom, we can then specify a particular atom by specifying the number of protons and number of neutrons it might have. While atoms can gain and lose electrons at will, rendering them ions, either cations if they're positive or anions if they're negative, the electric structure of the atom does not define its nature. And in fact, we recognize this in our terminology because we identify the number of protons as the element. Okay, so when we talk about an element or an atom of hydrogen or helium or calcium, this is solely determined by the number of protons. That element and its fundamental nature is due to the number of protons. And we'll talk about why and sort of why we're sort of privileging the protons as we move forward. In this symbol, in this symbolic structure, the symbol X is used for the element. Notice that there is no element X. There is an Xe, that stands for xenon, but there is no element X, so this is just a generic symbol. And we will often write the proton number, or the number of protons, with a Z in the bottom left-hand corner. Now, some important things to note. First of all, no chemists call this the proton number. This is most commonly known as the atomic number, which for a lot of reasons is quite vague, and I will try to avoid. On the other hand, you will see it everywhere, in part because this is the historical name for this particular idea. I prefer proton number A because it lets you know immediately that we're talking about the number of protons, and because it is less likely to be confused with other important numbers and qualities of the atom. It is given the symbol Z or Z, and it is, importantly, contains exactly the same information as the element. So if you tell me the element, you don't need to tell me the proton number. And if you tell me the proton number, you don't need to tell me the element. They contain the same information. That is, the proton number determines the element. But in colloquial English, we discuss particular elements rather than naming them by their proton number. If a physicist were to reinvent the periodic table, instead of counting hydrogen, helium, lithium, beryllium, boron, carbon, etc., they would probably just name them after the number of protons. But here we are. So the element is given the symbol X and written here at the bottom left. You give the proton or atomic number with the symbol Z, and then up at the top left you give the symbol A, and the symbol A stands for the nucleon or the mass number. This is the total number of nucleons. This is referred to as a mass number, and this is probably the worst example of nomenclature in chemistry. The mass number does not tell you the mass, it simply tells you the number of nucleons. It's given the symbol A. So, if we think about hydrogen, hydrogen is a hydrogen nucleus with a single proton and no neutrons. Sorry, I should back up here. There's one more number that is not usually specified in the element, and that is the neutron number, which is simply the number of neutrons, given the symbol N. The neutron number, though, can always be acquired from A and from Z, because the nucleon number is the total number of nucleons, and the Z, the proton number, is the total number of protons. So if you take A minus Z, you always get N. So hydrogen is a hydrogen nucleus with one proton and no neutrons. It has a proton number of 1 and it has a neutron number of 0, giving it a nucleon number of 1 as well. It's important to recognize that this thing right here is just a proton. Okay? Helium has 2 neutrons, 2 protons, and therefore it has a nucleon number of 4 and a proton number of 2. And a higher example, lead, significantly larger, has 82 protons in its nucleus and 210 minus 82 neutrons, giving a nucleon number of 210. Therefore, a neutron number of 128. Each one of these things is strictly speaking not an atom. They're strictly speaking called nuclides, which is a new term that refers to a nucleus with a specified number of protons and neutrons. So there can be different nuclides of, let's say, hydrogen. Why? Because hydrogen can have different numbers of neutrons. Hydrogen can have no neutrons, or it could have 1 neutron, for example, making a what is called an isotope. So nuclides with the same number of protons but different numbers of neutrons are known as isotopes of one another, and each individual isotope, which is sort of a weird expression, but individual isotopes are known as nuclides. So that's a new bit of terminology. Most chemistry instructors and most chemistry classes, you'll just be using the word isotope to refer to the same thing. Strictly speaking, though, different nuclides can be isotopes of one another, but the noun for the particular specified number of protons and neutrons of an element is nuclide.